Hey guys, welcome. Yeah, so I'm gonna give you our very first example of variation of parameters, and I strongly encourage that you watch example 0, the concept video, because it shows you where this formula comes from, it shows you where this formula comes from, and it explains a lot of other things. So for you to so you completely understand variation of parameters, I really think that you ought to watch example 0. Anyway, variation of parameters is a method we use for solving non-homogeneous second-order linear differential equations. So let's see it at play. So what it does is it helps us find a particular solution, right? And let's say that the particular solution is called yp. Then we're saying that yp will equal like some v1 times y1 plus v2 times y2, v1 and v2 given by these two integrals, and y1 and y2 being the complementary solutions, right? So let's say that the complementary solution is written as yc, then yc is like alpha y1 plus plus beta y2. And you should recall that the complementary solutions solve the homogeneous equation, right? So if this equation, instead of equaling sec x equaled 0, right? If it equaled 0 on the right side, then it would be the homogeneous equation. And so y1 and y2 are the solutions to the homogeneous equation. And in the method of variations of parameter, it is required that you have already figured out what y1 and y2 will be. And that's because we're going to construct the particular solution using y1 and y2. Yeah? All right, cool. So we have v1 to calculate and then v2 to calculate. Let's get on with it. So v1 equals the integral of, well, as I said, we need y1 and y2, and y1 equals cos x is good, and y2 equals sin x is also good. And of course, y1 and y2 need to be a fundamental pair of solutions, and I explain what that means in example 0. So another reason for you to watch example 0. All right, cool. Anyway, they are a fundamental pair, and all it means really is that the Wronskian, that what I circled, isn't 0, and yeah, and we need to calculate it soon, so you'll see what the Wronskian is, which I also explain in greater detail in example 0. All right. Anyway, v1 is equal to negative y2, so in this case, negative sin x, right? And then times f of x. And f of x is just the function on the right side of the equal sign whenever the coefficient of y double prime is 1. And clearly here, the coefficient of y double prime is 1, so f of x is just sec x. Yeah, so I explained that in greater detail also in example 0. All right, I'll stop being abusive. And then sec x I'm going to choose to write as 1 over cos x. And I can, right? And then let's figure out what the Wronskian w of y1, y2 is. So w of y1, y2 is the determinant of the matrix with entries of y1, y1 prime, and then y2, and then y2 prime, right? It's this. That's what the Wronskian is. It's this determinant. Well, we know what y1 and y2 are, so we can get to y1 prime and y2 prime. So y1 is cos x right there, right? So we have cos x. So y1 prime is negative sin x. And then y2 is sin x. So y2 prime is cosine x. And the determinant of this matrix, which is our Wronskian, is cos x times cos x, that's cos squared x, minus, and then it's negative sin x times sin x, and that's negative sine squared x, and this clearly is equal to 1, right? All right, because that's cos x cos squared x plus sine squared x, which we know to be 1. All right, so the Wronskian is 1, which is very convenient, right? Because it simplifies a lot of our work. So here we're just dividing by 1, which we might as well not do. And then we have dx, right? And then now v1 is going to equal the integral of negative tan x dx. And the integral of negative tan x is the natural log of cos x. So there we are. Now we can write a plus a for a constant a, but I explain in example 0 why we don't need to do that. But I'll explain it one more time in this example 1. So I'll leave the constant. I should do it without the constant, but I'll leave the constant on and show you why we don't need to write the constant, although I explained that already in example 0, the concept video. Anyway, we've got our v1. Let's move on. So v1 is equal to ln of cos x plus a. Got it. And then now we need to calculate v2. v2 is given by the second integral down here, and it's y1, which is cos x, times f of x, and f of x is again sec x, which we're going to write as 1 over cos x. Nice. And we know that the Wronskian, which we already calculated, is 1. And then that's dx here. So v2 is just the integral of, these guys take care of each other. So it's the integral of dx, which is just x. And so let's say it also came with the constant b. So it's x plus b. Nice. So v2 is x plus b. Got it. v2 equals x plus b. Now that we've got v1 and v2, including with the unnecessary extra constants, let's look at what yp would be. Yp would be equal to, as of right now, yp, and eventually, yp is going to be v1 y1. So y1 is right here, cos x. That's cos x times y1 times v1. And that's natural log of cos x plus a, and then plus, and then it's going to be y2 v2. y2 is sine x, right? So sine x times v2 is x plus b. Okay, let's look at this, and remember the general solution, y general, so this is all of the solutions to the differential equation, would be formed by adding the particular solution and the complementary solution. So let's pretend like we found the particular solution without the constants a and b attached to v1 and v2 respectively, and so then the complementary solution then, or sorry, the particular solution then would have looked like yp is equal to y1 cos x, still this, right? Cos x times v1, which is ln cos x, and then plus y2 v2. y2 is sine x, and v2 is x, so x sine x, right? We would have had that particular solution. And then, of course, by this, we had the complementary solution being yc. So yc is equal to alpha times y1, which is cos x, and then plus beta times y2, which is sine x. So then our general solution, which is the particular solution plus the complementary solution, would have been equal to, the particular solution is right there. So that's, I'll actually copy and paste it to save time. So it would have been the particular solution plus the complementary solution, which I'll also try to copy and paste. Sometimes this tool fails me. Let's hope it doesn't here. It does fail me. You see, I told you I'm not lying. You just proved that I'm a truth teller too. Alpha times cosine x plus beta times sine x. Yeah, and that also I can predict the future. Anyway, so if we went with this instead, right, with this answer that we had found a little bit ago now, then we would have written cosine x times natural log of all this, just to explain why we don't need the constants a and b. Otherwise, we were done a while back. Plus a cos x plus x sine x plus b sine x. Wait, this plus this is our complementary solution. It's included in our complementary solution. So that's why we leave out the a and the b and the particular solution. And of course, the rest of what we have, once I crossed out what came from our complementary solution, which is these two, once we cross those two out, what we have left, which is that plus that, is our particular solution, right? Which is right here. Yeah? Cool. All right. And as you can see, like the sum of these two actually mimics the form that we've written for our complementary solution. All right, cool. The next couple of examples will be briefer. I'll explain fewer things, but I'll walk you through each example in detail, and they get a little bit harder, so keep watching.